For this example, we're going to look at a couple of quadratic functions, both of which have a leading coefficient. So I'd like to turn your attention here to the fact that for the first example, there's a leading coefficient of 2, and really the thing that we're paying attention to is that the leading coefficient is not plus or minus 1. We just need to be a little bit more careful in that situation. In a lot of ways, our approach is going to be exactly the same. Our goal is still the same, and that is to get it into this format. So a times a perfect square, which we're calling x minus h quantity squared, plus k. And the approach is going to be the same. So we're going to start by factoring out the leading coefficient. So factor out. I'm going to say 2 here just because that's my leading coefficient, but in the next example, for example, it'll be -3. And you know what? I'm actually going to add one other thing here. So because we're going to be completing the square, and we do that on the first 2 terms, I'm going to go ahead and say, let's factor the 2 out from the first 2 terms. So that leaves us with 2 times x squared minus 4x. And again, I'm completing the square on this, so I'm going to leave myself a space and plus 1. Okay, so 2, I'm going to call this step complete the square and neutralize. Right? So what this step is really getting at is the fact that you can't just go around adding things to your function. That changes it. You all know that would cause a shift up, for example. So if we're going to add something, we also have to make sure to take it away. So what would we add to x squared minus 4x to complete the square? Well, you would take the -4 divided by 2 and square it, and you would get 4. So you need to add 4 to x squared minus 4x. But what did you really do? So notice that there's this 2 on the outside, and that 2 is being multiplied by that 4. So even though we added 4 inside of the parentheses, we added 8 altogether. So to neutralize what we just did, we have to subtract 8 off. I'm not going to go through the whole process here, but I'm just going to make a little note kind of here as an invitation for some of you. What you could do is make sure at this moment that all of this, 2 times x squared minus 4x plus 4 plus 1 minus 8, is the same as what you started with. So the goal is to completely keep your original function, but write it in this new form. So it's not a bad idea to check that, in fact, you did neutralize, that you did end up back where you started. Okay, so let's actually write it in the complete square form. Oops, let's go back to our purple color. So we have 2 times x minus 2 quantity squared minus 7. Okay? Now, think transformationally. I always say, when we're talking about the vertex, think transformations. So we have a stretch vertically by a factor of 2. That doesn't really do anything to the vertex. It just makes the parabola narrower. It makes it taller. Then we have a shift to the right by 2 units. And then we have a shift down by 7. And the shifts actually do impact our vertex. Our vertex started at the origin, right? Here is the vertex of the original function. So when we shift that right 2 and down 7, we end up there. So that point to -7 is the new vertex. Notice that there wasn't a reflection, so the parabola did start opening up. It continues to open up. So the vertex is still a global minimum, just like it was to start out with. And now let's go ahead and write that all out. So the vertex is the point 2, -7. It is the global minimum, just like it was on the original function, f of x equals x squared. The axis of symmetry. So I always want you all to remember that the axis of symmetry for a parabola is the vertical line that passes through the vertex. So in this case, it's the line x equals 2. The domain is all real numbers. All quadratic functions have an all real number domain. So you all are probably going to get pretty sick of doing this time and time again. But the range is very dependent on the vertex. The range, since the vertex is a global minimum, starts at the y-coordinate of the vertex and then goes up from there. For the intercept, so I think you all remember at this point, I like to lead with the y-intercept because it's quick to see. Looking back at the original function before we put it into vertex form, the constant term is all that's going to be left when we plug 0 in for x. So the y-intercept is the point 0, 1 because the constant term is 1. For the x-intercepts, so I hope you can see sort of graphically that there's going to be 2 of them. Even if we did a very, very rough sketch, you could see that with a vertex here and a parabola that opens up, you'd have vertices like this. You would have 2 of them, right? So we know there's going to be 2 of them. So let's find what they are. So we're going to take our function 2 times x minus 2 squared minus 7 is equal to 0. We'll add 7 to both sides. We'll divide both sides by 2. And now we're asking whose square is 7/2. So x minus 2 is plus or minus the square root of 7/2. And finally, to get x by itself, we add 2. And there they are. The x-intercepts are 2 plus or minus the square root of 7/2. You could rationalize the denominator here if you want. I'm not going to go through that process just because I want to save the time. But if you are interested in how to simplify this a little bit further, you can. So there are 2 x-intercepts. One happens when x is 2 plus the square root of 7/2, and the other one happens when x is 2 minus the square root of 7/2. All right, let's do our last example here. So here we have a quadratic function where there's a leading coefficient that's negative, but it's not -1. So the leading coefficient is not plus or minus 1. The only reason I'm pointing out that it's not plus or minus 1 is that when you encounter examples like this, they're a little bit more delicate. So I just want your your spider sense to be peaked there. Just like before, the goal is to end up with a form like this. That's called the vertex form. Some texts will even call it the standard form, but I prefer vertex form. So let's see what we have here. Just like in the previous example, we're going to start by factoring the leading coefficient, which is -3, from the first 2 terms. So we get -3 times x squared minus 3x. Then I'm going to leave myself a space here, and then minus 2. Okay. Now for step 2, we're going to complete the square, and neutralize. So remember how we complete squares. We take our middle term, middle coefficient, divided by 2 and square. It so happens that the middle coefficient here isn't even. So when you divide -3 by 2, you get -3/2. And when you square that, you get positive 9/4. So we're going to get plus 9/4 in order to complete the square inside the brackets. And then we have to neutralize. Well, what did we do? We added 9/4 inside these parentheses, but the parentheses are being multiplied by -3. So in fact, we didn't add 9/4, we subtracted 27/4, which is 3 times 9/4. And in order to neutralize, we have to add the 27/4 back in. What some of you may find helpful to remember here is that 2 is 8/4. So what you have here, and I'm actually going to write it in the next line down, you have -3 times x minus 3/2 quantity squared minus 8/4 plus 27/4. Okay, and that ends up being plus 19/4. Okay, good. So in terms of transformations, this is important. The fact that there's a negative on the outside means that there is a reflection in the x-axis. So in other words, if we started with a parabola that opens up the way that x squared does, when we reflect it, we are now going to have a parabola that opens down. So in this instance, the fact that there is a negative here tells us that the vertex is a global maximum, not a global minimum. So we're going to include that in our transformations. Reflect in x-axis. You also have a vertical stretch. That doesn't have much impact on the vertex. The fact that there's a 3 there. That just means the parabola is steeper and narrower. But again, while it impacts the shape of the graph, it does not impact the location or the kind of point that the vertex is. And then we have a shift to the right, 3/2 of a unit. And shift up, 19/4 of a unit. If you want to be writing these as decimals, you can. I generally prefer that you write them as improper fractions. I think that it's good to be comfortable with the notation, but I'm not going to penalize you one way or the other. Except, of course, if the decimals aren't precise, please never round. Always give precise answers. So if the decimal is non-terminating, please state it as a fraction. Okay, so the vertex. This is an exciting moment. The vertex is at the point 3/2, 19/4. So again, we took the origin, which was the original vertex, and we shifted right and up. So that location is our new vertex, 3/2, 19/4. And in this case, it is the global maximum. So in other words, since the vertex is about here, the parabola looks something like this. So there are still 2 x-intercepts because the vertex sits at the top of the parabola. So something like this. This is a very rough sketch. It's actually narrower than that. Okay, so axis of symmetry, domain, range. So the axis of symmetry is always the vertical line that passes through the vertex. It's x equals 3/2. And the domain is all real numbers. So that much is not terribly dependent on a lot of the particulars. Now the range. So notice that because the vertex is a global maximum, the range starts at negative infinity and then comes up to the y-coordinate of the vertex. So the range is from negative infinity to 19/4. Don't forget to include that y-coordinate of the vertex. For the intercepts, so the y-intercept is always a good one to start with, because all you need to do is look at the function before we did anything to it and find the constant term, which in this instance was -2. So the y-intercept occurs at the point 0, -2. For the x-intercepts, we know there's two of them. We've already kind of visualized the graph. So I always use the vertex form for this. So we have -3 times x minus 3/2 quantity squared plus 19/4 is equal to 0. So I have -3 times x minus 3/2 quantity squared is equal to -19/4. Now I'm going to divide both sides by 3. And I hope you all remember that when you divide by a number, it's the same as multiplying by its reciprocal. So since we're dividing by -3, it's the same as multiplying by -1/3. Nothing reduces except the negatives. So we're left with 19/12. So that's x minus 3/2 quantity squared. So x minus 3/2 is plus or minus the square root of 19/12. So my two x-intercepts occur at 3/2 plus and minus the square root of 19/12. So there are the two x-coordinates of the y-intercepts. Excuse me, the x-intercepts. So in summary, whenever we're given a function that is not already in vertex form, the process for putting it in vertex form is essentially the same. If there's a leading coefficient that's not 1, we factor it out. It might just be -1, or it might be some other number that's not 1 or -1. So we factor out the leading coefficient from the first two terms, like we did here and like we did here. From there, we complete the square and neutralize. And especially when you have a leading coefficient that's not equal to 1 or -1, be especially careful with how the leading coefficient interacts with the number that you needed to complete the square when you're neutralizing. When the leading coefficient is 1 or -1, that work is less. So it's especially important to be paying attention to leading coefficients that are not 1 or -1. So that concludes this lesson. In the next lesson, we'll talk about summarizing this to make it almost into a shortcut. So we'll look at the generic quadratic function, and we'll actually come up with a shortcut for where is the vertex of a generic quadratic function located. Stay tuned for the next video. Talk to you soon. Bye.